Oh, hello everyone, I'm Pankaj. Uh, that I'll talk about the program synthesis for artifacts beyond programs, and I'm a PhD student at IIT Kanpur, and I'm working with Doctoral. Okay. So recently the program synthesis is becoming very popular. There are lots of sophisticated algorithms, there are lots of sophisticated tools are coming up, which so the problem of program synthesis is that there is a specification and there is a, a language where language is a set of programs, you can define that, and then there is a synthesis engine which tries to find a program from this DSL and which satisfies a given specification. Now, and this satisfies the regular program. Now, what we mean by regular program here is that a sequential imperative sequence of instructions, like a sequence. Now, my talk is about the program which are beyond regular, which are not regular programs. So, for an example, you can think of this complex concurrency construct, like fences, like atomic section. Okay. Another construct we can talk about the sparsing engine. Now, top of it, there is a we can also talk about synthesis of abstract interpretation engine automatically. Now, these all three works have been published in various conferences. So this the third one is Oslo 2020. Okay, let's see what's the main theme of my work is there. So we have some non-regular or beyond regular synthesis program. So what we do, that brown box is the what I do. It's a high-level algorithm of my own work. Is that we convert this problem of beyond regular problem to a set of regular problem, regular synthesis problem. Sorry, and use the off-the-shelf regular synthesis engine, which is currently available, and try to solve the problem for the beyond regular synthesis problem. So we're trying to just convert it to some other problem and merge the solution to solve the problem. Now this works, this whole the algorithm, what we say, high-level algorithm has been used in all the three works. I'll go through it one by one. The first work, it's about synthesis of complex construct. This work has been published in CGO 2020. It's about it. Now take this a program. So there are two global, X and Y, and there are two threads, thread 1 and thread 2. So in this interleaving, if you see, there is a assert sitting there at this line number 8 in thread 2. So you see that assert is not violated in this interleaving because X and Y are both getting updated as 1. So in the end, while assertion say A and B are 1. Okay. Now look at this interleaving. Same program, but it's a concurrent program because and it has many interleaving. But in this interleaving, there is an issue. What is the issue is that since the updation of X is done previously, so when the thread 2 runs, this assertion violates because A is getting value from Y and B is getting value from X. Now B becomes 1 because X has been updated as 1. Now we see there is a assertion violation in this code. Now take this another program which is little bit similar, but this assertion is different. So it says assert A equals to 0 or B equals to 1. Now when can this program be validated? So the assertion must be false. So when it will be the case when A equals to 1 and B equals to 0. But if you look at the program, it's not trivial. I mean, it looks like that it's not possible. It's always satisfied assertion because to be A equals to 1, if you see, A takes from Y. So we assume that Y is 1, so we assume that X must be 1. So we always the case that B is also 1 because Y is updated later. But life is not so simple. So there is something called weak memory model where hardware and compiler supports. There are many weak memory models such as PSO, SC, and TSO. In PSO or partial store ordering, the two store can be reordered, and it actually happens in our real system. So now if you see, if you get flip this order, Y comes here, X comes there, it is same as interleaving. If you look at the previous interleaving, with the same interleaving, you can get these values. In the beginning, we thought it's not valid, but it can be validated. So, what we do? We found our solution. We built a tool called Gambit, which automatically try to synthesize atomic section and Francis. Now the Gambit, the main core algorithm in Gambit is a first order theorem proving, where it takes the program constraint, how does the program look like, and the memory constraint, what type of memory is there, like TSO, and some, we want to talk about some behaviors which is possible in TSO, but not in SC, some kind of like that. The query, what kind of query? Now, for example, in this first problem where we have this assertion A equals to B, you see that if you make atomic section both is paratomic, then you will see it never violates because there will be no in-between interleaving. In the second case, so there is something called construct called source fence, which allows no reordering. It prohibits the reordering. So this is a two store, so it's equal to store fence. So if you put this fence, you cannot reorder. This fixes our bug. So it's called fence for. So we try to synthesize the fence. Now what we have done, this synthesis technique we have incorporated to a debugger. And apparently it's ZDB. So we made an interactive debugging tool. Instead of giving a program, we try to debug a trace of the program where the inputs are fixed. Then evaluation we have done in standard benchmarks, where in this tool we have given some features like repair suggestion, which you have already seen, try to repair, try to add some atomic section or fences. And we have also add something called differential debugging. What it says that, can you give me some value which is possible in some memory model but not in other memory model? So why this question is important? Because you might be coding in one computer and you're shipping that code to someone else who is running on something different. He might be experiencing the problem, but he might not. So sitting in your laptop, can you fix it out? Can you model his PC in your laptop? We have for this business benchmarks, we have taken about more than 100 traces, and we found that it was pretty fast, to be around 1 second, which it is used to say it's good for interactive debugging. Okay. Now let's talk about the second word, which is the synthesis of semantic action inverse. So as the previous talk, we talk about the strings are everywhere. So we take out this string, we don't know what is the operations, then there are some values to this. How we get it? So while parsing this, the grammar, contextual grammar, to parse the string, we can associate some semantics to this grammar. Now this is called attribute. For each non-terminal of the grammar, you can add some attribute and give some semantics to the grammar. So while parsing, we can also evaluate on some grammar, so on the string. So in this case, the string gives the value. Now what our contribution is, so you see, right, when I ask the question, it's like re-declared again. So what we say, this semantic action is missing, given the grammar, and given a set of input-output relation. So this is a specification that for this string, the output should be like that. Can we synthesize the semantic action on this? That's the whole work is about. Now, what motivates us to do that? So if you see, we have seen that from the strings, we can get to the values, but we have also seen that from the strings, we can get to the ASP. In our paper, we can see we have done a case study on the spin model checker. So the spin model checker, the parsing technique, it's there in here. So it has, in semantic action, is trying to create an ASC while parsing the code. So we are able to synthesize the ASC part, the code which creates the ASC. Then we have also tried to synthesize the actions for a Java interpreter. So this is the Java interpreter code. Can we do what push looks like? What is the add looks like? We're able to synthesize that. Now let's discuss about one interesting problem we have able to synthesize. It's called forward differentiation. So the forward differentiation says that you can do fx and f prime x. Like fx is at x equals to some constant. You can do that simultaneously. You don't have to. It's a technique where to do the f of x and f prime x at the same time. So we are able to synthesize the operations for both fx and f prime x for these operations: add, subtract, multiplication, cost, and power. This is one of the interesting. Even the whole paper is the motivation example is on this. You can read it. Okay, now coming to my third problem. So we have talked about the synthesis of uh, um, concurrent programs constructs, the synthesis of semantic actions. Now we'll talk about the synthesis of transformers. So this talk, sorry. So I have talked in the last talk. I don't know why I'm always the last, but so this is the last talk in the synthesis track. You know, so yeah, so you all know about this concrete abstract definition where there is one concrete domain, and there is an abstract domain. I have some Java connection for this both domains. Now, what is the problem is that suppose in case of concrete domain, when you apply an operator f, you have to define what will be the operation in the abstract domain, the abstract. So when you we have to, otherwise we are able to write it manually or some to over approximation and all. But it's tricky even for any trivial operation for to write the abstract transformer for any simpler domain itself. And they are very wrong. You can make a mistake at every step. So let's try to look into the absolute function, which just like whether given a negative number, also you can map it to positive number and try to build an interval domain. Interval domain says it has two elements, left limit and right limit. But if you see, assuming you don't use if else, so the solution for this is pretty tricky. It's not very straightforward. Even the for absolute operation in interval domain is pretty tricky, and we have another solution which is much trickier than this. No, so we try to we created a tool called Amut, which so when synthesis is a transformer, it should be sound and it should be precise. So in our algorithm, there is a soundness SEGIS loop. SEGIS stands for counter example guided inductive synthesis. So we generate a positive example in case of soundness check, and we also have a precision loop, which checks for a precision, whether my transformer is precise or not, if it's not refined again. So we have, in the end, we have two loops, which not simultaneously, it runs one for the soundness check and one for the precision check, and try to synthesize this transformer. There are, it's not that simple, but yeah, I'm keeping it trivial for this presentation, and I'm requesting you to attend the talk for the more information on this. So what we have done for this to test whether we are able to synthesize the correct transformer or not, we have done two case studies. One is on the string domains and one is on the interval domain. So we take about 5 domains in string and around 3 domains in interval. So our transformers have same runtime as the mutual manually written one, and we have found 4 soundness bug in 2 real-world abstract integration frameworks. So the manually one has bug, and what we have synthesized, they are like sound, and we're able to verify it. So what's next? So solve more such problems, which beyond, so synthesize programs are beyond regular programs. Okay, for last, I want to thank Google for giving the travel ground to attend this training. Thank you. I'm happy to take any questions. Yeah.
So I guess let's start with the next part. So what could be more such?
Yeah. Thank you. So the first of the gambit I talked about, right? A concurrency constructs. The one we are thinking of to use this, it's an interactive decoder. It's like GDP. You add the query, you run the code, and you add query. Okay, is there something, the different, is there any value which is possible in PS or not in PS, something like that. It's an interactive decoder. You talk to each other. So can we use that to teach memory model for a course? Like if students say, okay, delete this line, we have add a fence on a fly, not compile again and do on a fly. And even for the, now you see, if you teach the memory model, you have to find some questions, right? Okay, find a bug in this memory model. Given the memory model, given the program, can you give me a trace where there is an issue in SC, is in TSO but not in SC, something like that. Can you automatically synthesize those questions for the teacher? In it is for the pedagogical reasons. So, and the third one, the more, the one we are doing, it is not similar, I say, but non-relational, I can say. So, can we do it for relational? That's the possible direction.
Okay, so in a sense, it's more about the tooling around the existing things now.
Yes, so can we use the existing things to solve not existing things? Yeah.
Yeah, so really nice work, interesting synthesis problems, seems very effective. One comment, and I'm going to reveal myself as reviewer too by my comment, but the kind of the selling, I'm thinking about your theme of your dissertation, right? And
yeah.
Your selling point is program synthesis beyond programs. Broader hexagon programs. To me, these are programs, but I do see that you're reaching beyond kind of normal synthesis.
Yes.
So I'm just trying to make a suggestion. And so one thing I thought of, which was not in YouTube, is you might think about maybe something like specializing synthesis to different domains.
Okay.
Because what I see that's kind of unique in your work is taking constraints from a given domain and kind of integrating that into the synthesis in ways that would be unique to the domain and not applicable,
Okay.
to sort of ordinary program synthesis.
Yeah.
So that might be a way of putting it. Might in some ways it might even be a more positive spin on it.
Yeah.
Anyway, you're in charge of how to sell your work.
No,
just a suggestion. So
yeah, thank you for this.
Yeah, I have a question. I wonder, you introduced the three words about synthesis. I wonder the technical detail. I mean, I know that these three words share the similar aim is going to do some synthesis on the program, but they are doing some synthesis on a different setting. For example, the weak memory language or some others. I wonder whether their technical detail is totally different, or is there something similar to do that?
So that's what the flowchart I have. It's a high level algorithm, not an algorithm. So it's not like that we use the same technique for all. Like in this case, there was like 2 loops, but in other case might not be there. But the thing is that the whole idea is like there are some problems which cannot be solved by Sketch or Rosette or something. But can we use Sketch or Rosette to do that in other way? If it's that answer your question.
Okay, thank you.
Okay. Any more questions, comments? Right. I know it's a bit late. So, sorry. I also did not plan to make you second twice.
I'll add a question. In the weak memory model, is there a specific reason that you're looking at TSO or?
Well, not TSO, yeah.
Are they easier to analyze in some
Yeah,
sense,
so
or-
in the another thing we can do in the future after doing the C++ weak memory consistency, right? But thing is that You have to model the C++ weak consistency model.
Which
So-
is more complicated.
More complicated.
Yes, but you can take the release require fragment, which is
Yeah.
complicated, but it's okay.
Yeah, means that's one way to do a feature. I forgot about that.
Okay.
Feature.
Um,
Uh,
Yes, continue. I just, I don't know, I think you, maybe it's too complicated to explain, that's why you didn't explain exactly how it works.
Yeah, sure. Because keywords, right? I need to engineering. I don't know how.
Yeah.
But I'm here. You can talk.
Okay. Should we tomorrow?
Yeah, until 10. My talk is the last. Yeah, you are.
Yeah, just I have a very minor problem. Could you change the slide to the weak memory, that example at the beginning? Like I remember there is an assertion to say A equals to B
Yeah.
sometimes.
Yeah. And
Uh,
sometimes it changes to something else.
Yeah, the previous one.
Yeah.
Since I mean, even if the it's not with memory, since
No, it's not with me.
Okay.
Normal interleaving
Yeah,
program.
normally it still happens sometimes when A not equal to B. That's what you mean.
So this assertion will be validated. That's what my point is. Means in this assertion, how to fix this assertion. So the way to do is atomic blocks. That's a motivation.
Okay.
It's a by example. Just.
Okay. Thank you, Pankaj.
Thank you.
Thank you.